Hello, I'm Adeya Anugu, and this is my final physics presentation. So the goal of this lab was to compare the experimental and theoretical times that it would take for an object to land on the ground on the moon. We're interested in this because we can use Newton's momentum principle and expect the experimental and theoretical models to show the object hitting the ground at the same time, due to there being no air present on the moon. The physics principles used in this lab mainly come from Newton's second law, which is the momentum principle. In this, we say that F net is equal to the change in momentum over time. Then, we can integrate dp dt twice with respect to time to receive this equation, which states that the change in y position is equal to the initial velocity times time plus 1/2 times the acceleration times time squared. Then we can rearrange this equation to solve for time, which would be square root of 2 times the height that the object is dropped from divided by the acceleration due to gravity from the moon. Based on the equations derived from the previous slide, we can predict how long it would take for the hammer on the moon to fall to the ground, assuming that it's dropped from a 0.87 meters off the ground and the acceleration due to gravity is 1.62 meters per second squared. We should expect this equation to yield the same time as the experiment, considering that there are no other forces acting on the hammer as it falls to the ground due to a lack of drag force, as a result of a lack of air on the moon. Then, using the equation we got from the previous slide, we can say that t is equal to 1.04 seconds. Before we go over the actual experiment, here are some references. Using the data we got from Tracker, we can compile this graph, which is the y position on the y-axis and the time on the x-axis. So the theoretical time that we calculated from the experiment would be 1.04 seconds, but the actual time it took for the hammer to hit the ground was 1.001 seconds. The results from the experiment indicated that the estimate for the time it would take for the hammer to hit the ground on the moon was very close to the actual time it took, considering there was only a discrepancy of 0.039 seconds. The difference between the experimental and theoretical times that it took for the hammer to hit the ground likely was due to a tracking error in the video analysis. I had a particular difficult time putting the point mass in each frame in Tracker considering how blurry the video was. Additionally, I set the calibration of the hammer to an assumed 35.56 centimeters, which may have not been the actual size of the hammer. This was because the size of the hammer was not specified in the video, and 35.56 centimeters is a standard size for a hammer. Hence, given a clearer video with the specified size for the hammer, the experimental and theoretical models should yield the exact same time for the hammer to drop. Thank you for watching.